Equilibrium Vodcast number 2. This will be a short one just to get us through the first type of calculations for an equilibrium constant. All right, starting at section 15.4, let's talk about the fact that there's different kinds of equilibria. Sometimes they're heterogeneous, in which you have different phases of matter, and sometimes they're homogeneous. So if you have reactants and products that are all the same, that's called homogeneous equilibria. If they're all gases or they're all solutions, that's the easiest to deal with. Those are the ones we've been talking about so far. If you have equilibria that's got a solid and a gas and maybe even a solution, that's called heterogeneous equilibria. So let's think of one example. The decomposition of a lobster shell in a compost heap. All right, so this would be the chemical reaction of calcium carbonate decomposing into calcium oxide and carbon dioxide gas. Notice we have a solid producing another solid and a gas. That's a heterogeneous equilibrium. So we'll need to assume that this compost pile is enclosed, like this bell jar, so that everything can remain available for forward and reverse reactions. Now that would result in an equilibrium constant being produced only by looking at the concentration of the CO2 gas or the pressure of the CO2 gas. Either way. Well, why is that? Why aren't the solids included? As I've said here, pure solid or pure liquid is not involved. If you can imagine a confined space in which the amount of lobster claw is great enough that it doesn't all completely decompose, there's always some solid there, then adding more lobster claw will not change the equilibrium amount of CO2, because the amount of CO2 available is going to be limited by its space and the conditions of the system. Once it reaches equilibrium, that CO2 amount won't change, even if you add more lobster claws or even if you take out some calcium oxide. That's not going to change the conditions that the gas needs to have a certain concentration. So in general, you leave out pure solids and pure liquids, such as a water that's a solvent, out of the equilibrium expressions. That makes it simpler, and it just focuses on the things that are affected most by the equilibrium conditions. All right, so now how do we calculate one of those equilibrium constants? These are the steps, and we're going to walk through them in an example. But first you want to tabulate everything you know. And then for anything you know where you start and where you end up in an equilibrium, you can calculate the change. How much change was there? Now that change is going to be stoichiometric. So you can use the balanced equation now to find all the other changes, even if you don't know how much you started with or ended with in some circumstances. Then you're going to use those concentrations and the changes to find out how much you have in equilibrium for each substance. So let's go through an example. All right, so you have a closed system initially containing 0.001 molar hydrogen and 0.002 molar iodine at a certain temperature. It's allowed to reach equilibrium. Analysis of the mixture shows that the concentration of HI is 1.87 times 10 to the negative third molarity. We want to know the equilibrium constant at that 448 degrees Celsius. So here's what we know initially. That the reaction is H2 plus I2 yields 2HI. And we know the initial concentrations of the reactants and that we don't have any product, and we know how much product is left at the end. So the first thing we can do is determine that our HI must have increased by 1.87 times 10 to the negative third. Obvious. from 0 to there. That can help us figure out how much the hydrogen and the iodide change because it's stoichiometric. So if this gained 1.87 times 10 to the negative third, these must have lost half that amount because the reaction says that H2 plus I2 yields 2HI. So for every 2 HIs produced, 1 I2 and 1 H2 is lost, so half as much. So therefore, now that we know how much hydrogen is used up and how much iodine is used up, we can figure out how much hydrogen iodine is there at equilibrium. So once we know the amount at equilibrium, we can then plug those into the equilibrium expression, Hi squared over hydrogen times iodide concentrations, and we get a concentration of 51, a equilibrium constant of 51. Okay, we're going to stop there so that you can practice some of these equations. These are fondly called ICE formula problems, ICE, initial change equilibrium. We'll practice some more in class, and I'd like you to try the first 5 problems in your homework set. Take care.